Wait, who does the intro?
Oh, I do. Okay, so hello. This is our CS225 final project. Justin.
I'm Tom.
I'm Venya.
I'm Ishika.
And we did our project based off of a Twitch user data set. And so there we go. So our goals for this project were basically to map the different degrees of separation between each Twitch user. And this would help us, this would help us determine like who exactly were the central Twitch users. And to do this, we implemented BFS, Dijkstra's, and betweenness centrality.
And so for the graph data structure, we decided to go with a vector of nodes and a vector of edge pointers. And you can see here, right here is the implementation for the nodes where we have where it stores the Twitch ID, and then essentially can be seen as a Twitch username, right? And then it has the coordinates of where they live, and a vector of edges. And those are indices that point to the edge pointers, a vector of edge pointers. And so for edges, we have a to and from, and then the weight, which is the distance between them. This is a undirected graph. So technically speaking, to and from are the same thing. So to work around that, we added a function to help get the adjacent node with the given node, right here with the helper function right here.
And so going off of what Tom said, we decided to parse our data into firstly a vector pair of ints, and this is to help store all the data for the edges. And then we also decided to parse our data into a vector pair of a pair of ints and a pair of doubles. And this is for users, and this is for keeping track of our Twitch users. And so the first pair would include our Twitch users' new ID and old ID, and the second pair of doubles would include the weights that we added on our own. So
just to cut in real quick, the new ID is the indices within our vector, and the old ID is essentially the Twitch username, essentially.
So yeah, and so kind of going, Tom mentioned this a bit earlier, but the data set actually doesn't have its own weight, so they don't have their own weights. So we added our own. And this was just to show like a proof of concept and to make sure that all of the data structures we implemented actually make sense and work.
So the traversal we chose to use for our graph was a BFS breadth first search, and the data structure we used to implement it was a queue, and it traversed our subgraphs with our nodes and edges and returned a vector of ints, which stored each of the indices or the old IDs to the node, or our new IDs to the node of the array in our graph class.
So we decided to make use of Dijkstra's algorithm to implement or to find the shortest number of degrees of separation between two users, which was essentially the shortest distance between two users based off their locations or their coordinates. So in our implementation of Dijkstra's, we made use of two separate maps, which were respectively for tentative distances and for a map of the previous nodes while we were traversing through the set of nodes, a set for visited set, and then a priority queue. So our implementation of Dijkstra's took in the Twitch ID of a source node and the Twitch ID of a destination node and returned a vector of the nodes the algorithm traversed through.
So in order to implement our betweenness centrality algorithm, we took the Dijkstra's, or shortest path from each node to the other, and calculated the betweenness factor of an original node, which was considered to increase each time the node was found within the shortest path. And then we calculated the greatest betweenness factor amongst all the nodes, and that node was considered the central node and had the most ties to other Twitch users and mutual followings. We then returned a Twitch ID of this central node and completed our betweenness centrality.
So in conclusion, we essentially were able to achieve everything that we set out to do within our original goals. We are able to derive the shortest path from user to user via Dijkstra's, and we were able to determine the central user via betweenness centrality. essentially our algorithms could be used to detect ties amongst users.
So just a few improvements for our project. One is to optimize our algorithms. Our Dijkstra between essentiality could have some work done on. But most importantly, I feel like BFS wasn't really used properly just because BFS traverses through the entire graph, which we don't want, which Dijkstra only traverses through the graph until we find the end node. So I think a better way to implement BFS would be to use iterators and feed the nodes one by one rather than traverse through the entire graph. We can also improve parsing and data storage. So parsing right now, we couldn't really open a CSV file or work on that. So we decided to convert it to a text file. I feel like it would be a lot better if we could actually read in the CSV file and also store all the extra data that comes with it, because we can do a lot of cool stuff with that. And then one last thing we can do is improve our testing infrastructure, because the way we wrote test cases, we wrote them as we implemented each function. So they were kind of disjointed and like all over the place. And so each test case had like its own unique graph for it. So I think a better way of working on this would be to first write out all the graphs, like possible graphs, small, medium, large graphs, and then build our test cases around those graphs, allowing us to actually write like smaller, like helpful functions and like clean up our test cases.
So that was the end of our presentation. Thank you for watching.
Yeah, thank you.